All right, let's continue with 6.2 homework. So this is number 57. Find the growth model for Bulgaria and let t equal 0 represent the year 2000. And so we can go ahead and plug in the information here. Now the table does give us provided information that in 2001 that there are 7.7 million people in the population. So and we know that t is equal to 0 can help us find the growth rate. So we don't have enough information to find c, but we do have an ordered pair that we can use to solve for k first. Okay, actually in this case our k value is provided for us, negative 0.009, sorry. So we're going to go ahead and solve for c. We're given that we know that the formula that we're going to be using for growth model is p is equal to ce to the kt. So our k value we can plug in, our ordered pair, time, we can plug in 1 in for t, we can plug in 7.7 in for p, and we can simply plug all this in and plug in the calculator to solve for c, and c will be estimated to be 7.7696. So that is our specific equation. For part B, use a model to predict the population in 15. So in 2015, we know that means t must be equal to 15 because t equals 0 represents the year 2000. So we can simply plug 15 in for t and solve for p. So 15 in for 15 in for time, plug all this in, and we get p is equal to 6.788, and that will be millions of people. And part C is the population increasing or decreasing, and since our constant of is represented by a negative value, then we know that our population is going to be decreasing. Okay, let's continue on. This is number 71, Newton's law of cooling problem. Okay, so we see that it says the rate of change of temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So that is Newton's law of cooling. Okay, when an object is removed from the furnace and placed in a constant 80 degrees Fahrenheit, so this is the medium, the core temperature is 1500 degrees Fahrenheit. 1 hour later, the core temperature is 1120 degrees Fahrenheit. Find the core temperature 5 hours later. So the ordered pair that we'll be plugging in is represented by time followed by temperature. So we have a couple of order pairs that we can plug in. We know at time 0, core temperature is 1500. 1 hour later, 1120. And 5 hours later, we're trying to find out what the temperature is. So with these equations, we're always going to be setting up this way, where the rate of change of temperature is proportional, so k times, the difference between the object's temperature and the surrounding medium. So y minus and the surrounding medium is 80. So this will be the form that you'll be using whenever you see these types of problems. So we have our differential equation. So next step is we want to begin to solve for y. So separate the variables. Let's get the y's on the left, everything else on the right. So if we go through u substitution here, this is in the form of 1 over u, so we know we'll be using natural log. But I went through u substitution anyways. And the right side is simply just going to be constant k. So left side we get 1 over u. So 1 over u will simply give us natural log of u. In this case, the u is represented by y minus 80. The constant k, integral of a constant is simply constant times the variable t plus c. So we have this equation. Now we want to solve for y. So to solve for y, we want to get the y out from underneath this inside this natural log function. So I'm going to exponentiate both sides, which then will allow me to reduce, cancel out. The left side will simply be y minus 80. The right side, we can split into the product of two terms, e to the kt times e to the c. And we know that e to the c is simply a constant, so we can just pull that in front. So we get y minus 80 is equal to ce to the kt. Now we want to solve for c first. So we have the ordered pair 0, 1500. 1500 plugs in for y, 0 plugs in for t, and we just simplify, solve for c, we get 1420. So we have 1420 in for c. Now we can solve for k. So plug 1420 in for c. Now we can use the other order pair that we have to plug in. So 1120 plugs in for y, 1 plugs in for t. So simplify, we get 1420 is equal to 1040. Divide both sides by 1420, and we want to eventually get to k, but for now the 1420 is attached to e to the k, so move the 1420 over. 1040 divided by 1420 is 0.7324. Use your calculator there. Next, we want to get that k down from that exponent, so we're going to take the natural log of both sides. So once we have that, use the power property for logs to bring that k down in front. So k times ln of v is just going to be 1. So k is equal to natural log of 0.7324. So now we have the c value, we have the k value, so we have our specific equation. So once we have our specific equation, then we can plug in 5 in for time and solve for the particular temperature. So plug in 5 in for t, and we're simply going to be left with y minus 80 is equal to, and all of this can be plugged in your calculator, 299.247. Add 80 to both sides, and y is equal to 379.247 degrees. Okay, the last few problems here, 73 through 76. Okay, determine if the statement is true or false. In an exponential growth rate, the rate is constant. So we know that the rate is not going to be constant because if y is equal to c to the kt, here's our exponential growth function. And if we try to find the derivative, our derivative will be constant, will just stay. E to the kt, the derivative for e to the kt is e to the kt times the derivative of kt, which is just going to be k. And we know this won't be a constant because we have a variable in the derivative, so this is going to be constantly changing. Okay, something that would be a constant growth rate would be if it was y prime is equal to c times k. That would be something, but that would be a constant. But we have a variable here, so that variable is always going to be changing. This is not going to be a constant growth rate. Okay, for 74, in a linear growth rate, the rate of growth is constant. Okay, that's true. If it's a linear growth rate, then that growth rate is going to be constant. So it's going to always be increasing at a specific number, whether it's 3 or 4 or any constant value. 75, if prices are rising at a rate of 0.5% a month, then they're rising at 6% per year. Okay, that's true. We can use unit conversion to help prove that. So 0.5% per month, unit conversion, find a suitable ratio. So 12 months per year, this is equal. The months can cancel out, so 0.5 times 12 is 6, so 6%, increase of 6% per year is the same thing as 0.5% per month. Okay, finally, 76, the differential equation modeling the exponential growth is dy over dx equals ky, where k is constant. Okay. And if we take the integral of both sides, we have integral of dy over y is equal to k dx, and e to the natural, if we separate the variables and solve for y, we get y is equal to ce to the kx, and our k is going to be constant here. Okay, so that's our true statement.